Hello, welcome to this video. What I'm going to do is go through how to solve exponential and logarithmic equations, which are inverses of each other. So what I'll do is walk through this change of base formula, which is something that we're going to use and apply it later on to solve exponential equations. And then we'll go through a couple examples of actually solving exponential equations. We'll solve a couple logarithmic equations using exponential form, which is the inverse. We'll do a couple problems where we're going to solve using the intersection feature on a calculator. So that'd be by graphing. And then we'll end up doing a story problem at the end, which, again, traditionally what we've done is end up graphing a curve and then putting another value in for y and finding the intersection. So what we're going to do is solve it algebraically now using logarithms. So from the top we have this change of base formula, which basically says if I have log base a of some number which is n, I can rewrite it by changing the base of two log equations or expressions, and that would have the same base number. So you're changing the base to this b value, and this property holds true that if you take log base b of n over log base b of a, it would essentially represent the same thing as this log base a of n. So kind of a cool property that works with logs. What I'm going to do is go through an example of how to solve a log equation here. So what I have is 6 to the 3x power equals 81. So traditionally what we've done is go to the calculator and put in y equals 6 to the 3x, and that would give us a curve, and we would put in y equals 81, and that would give me a horizontal line, and we would go to the calculator and do second trace and find the intersection, and whatever that x value was would be our answer. So what we're going to do now is use logs because they're inverses to exponents, and we can use the logs to algebraically solve these equations. So in this example, I would first log both sides of this equation, take the 3x and swing it down as a coefficient to the log equation, and then what you would do is divide both sides by log of 6, and that's what's done here. And this part would go into your calculator. You would type in log 81 divided by log 6 and hit enter, and then you would divide by 3 and you would get this 0.8175. So a really quick, easy way to check that would then be to substitute it right back into your original equation, and you would end up with 81. So we're going to get some practice doing this. In this first problem, I have 3 to the 2x minus 3 equals 10. So the first thing I'm going to do is apply this log to both sides. So log 3 to the 2x minus 3 equals log 10. And then same thing that was done in that example, the 2x minus 3 I'm going to bring down as a coefficient. And then I'm going to rewrite that next to the log 3 and set that equal to log 10. So the next step then, I wouldn't want to distribute the log 3. We can divide both sides by log 3. And this is where we're going to go to a calculator. So this is going to go away then. And then I'm going to end up with 2x minus 3 equals some number. And that's what I'm going to get from the calculator. So what I'm going to do is take log 10 divided by log 3. And that's going to give me 2.096. And then what I can do is add 3 to that. So 2x is going to equal 5.096. And then divide that value by 2. So I'm going to quick add 3, divide by 2. So my answer is going to come out to, and the problem says round to the nearest hundredth, so I will leave this as 2.55. So x is going to come out to 2.55. And again, if we wanted to check our answer, what we could do is take 2.55 and substitute it right back up into the equation for x, and you would end up with a value pretty darn close to 10. It would be a little bit off just because of the rounding. The more decimals we would have rounded to, the more accurate our answer would have been. In this next one, instead of logging both sides first, what I'm going to do is add 3 to both sides, and that's going to go away. And I'm going to have 2 to the x plus 5 is equal to 11. And now it becomes a problem like the one that we just did, where I can now log both sides and say log 2 to the x plus 5 equals log 11. And apply that same property from before of swinging the x plus 5 down as a coefficient to the log. And then we're going to divide both sides by log 2. And that's the part that's going to go into the calculator. So I'll be left with x plus 5 equals that ugly decimal. So I'm going to go to the calculator, clear this out, and put in log 11. And keep in mind, close the parenthesis after that, otherwise you're going to end up with a wrong answer, because then it would be dividing log 11 divided by log 2, but it would do that all as one log, and it wouldn't separate them. So parentheses are huge. So this is what I would end up with, and then to solve for x in this equation, we would just have to subtract the 5. So this is 3.46, and then x is going to equal that number minus 5. So I'm going to subtract 5 on both sides, and end up with x equals negative 1.54. And again, we could substitute that right back up into x if we wanted to, and we would get something at the very end of this that'd be pretty darn close to 8. Alright, so what do we do if we have exponentially expressions on both sides that have an x in the exponent spot? So what I'm going to do is first log both sides of this and write it as log 4 to the 2x plus 6 equals log 3 of x plus 5. And I'm going to use that same property again, where we're going to bring these down as exponents. So I'm going to bring my 2x plus 6 log 4, and over here I'm going to have my x plus 5 log 3. Now this is where I am actually going to distribute. So instead of dividing both sides, which we could do, what I'm going to do first is distribute on both of these sides. And by distributing that value, what I'm going to do is go to my calculator and take this log 4 and this log 3, and what we're going to do is figure out what the decimal value is of those, and then I can distribute that. So what I'm going to do is take my log 4, and that's going to give me 0.602. So I'm going to do that, 0.602, and that's something I'm going to be distributing here on the left-hand side. And on the right-hand side, I'm going to do log 3 and figure out what that value is, and that's 0.477. And now what I'm going to end up doing is distributing. Which before I do that, I could even just divide this, just to make this a little bit easier on myself. I could divide this by either the 0.602 or the 0.477, and it would really essentially give me the same answer. So what I could do is divide both sides by 0.602 instead of distributing on the left side. So now I would have my 2x plus 6, and on the right side I would take 0.477 divided by 0.602, and that's going to give me 0.792. And then in parentheses I still have my x plus 5. So what I'm going to do is just distribute that on the right hand side of this equation, and I'm going to bring down the left hand side. So I have 2x plus 6 equals 0.792, and that would be x plus, and then I'm going to take that number and times it by 5, just for distributing, and that's going to give me 3.962. So now I just have an equation that has some x's on both sides and some whole numbers on both sides as well. So what I can do is subtract 0.792x on both sides. And then I can take 2 minus 0.792, and that's going to give me 1.208, and that has the x. And then I'm going to bring this 6 to the other side by subtracting. So I'm going to take 3.962 and subtract 6 on both sides. And that's going to give my right-hand side negative 2.038. So now my last step then would be to isolate the x by dividing by 1.208. And I'm going to get an x value of negative 1.687. Or if I round to the nearest hundredth, we could write this as negative 1.69. So in this case, this problem was different because we had exponential expressions on both sides. And what I actually did was log and get the decimal equivalent of these values. Whereas in the last problem, we ended up just dividing by the log on both sides first. So this one had a little bit more work to it. And this is actually the same example. We're going to end up solving this by graphing in a little bit, and we're going to get this same answer in the calculator. These ones, to solve these log equations and round the nearest hundredth, what we're going to do is write these in exponential form. So this 3 is my base number, this 3 would be my exponent. so I would write it as 3 to the third, and then writing exponential form would get rid of the log, and I would have 2x plus 1. So I'm going to bring that 2x plus 1 down. 3 to the third power is 27. I can subtract 1 on both sides, and then divide both sides by 2. So x equals 13. And that would be your answer for the first one. So these ones are a little bit shorter. And then for this problem, there's a couple properties that I would apply first so that we could express this as a single log. First thing that I would do is bring this expression down, and I would write this as log base 2 of 4 to the second power. So bringing this 2 value up as an exponent. And now what I really could do is condense these as a single log. So the fact that this is a subtraction in the middle and that I have the same base numbers really would condense down to log base 2 of 8x over, and then this 4 squared, which is 16, and that would be equal to 3. So all I did there is I turned the minus sign into a quotient, which was another log property, and the 8x would become my numerator, and the 4 squared, which is 16, would become my denominator. And now what I could do is rewrite this in exponential form. 2 is my base number, and 3 is the exponent. The left-hand side, the log is going to go away. Instead of having 8x over 16, I'm going to simplify this. 8 over 16 is a half, so I'm going to write it as x over 2. Okay, so it's the same thing as 1/2 x. And on the right-hand side, I have 2 to the third power. So x is really equal to, or I'm sorry, x over 2 is equal to 2 to the third, which is 8. And then if I wanted to isolate the x, right now it's being divided by 2, so I would have to multiply both sides by 2, and x would come out to 16. Alright, so now back to the problem that we had done a couple problems ago. We're going to solve this equation by graphing. What I'm going to do is go to the graphing calculator, and I'm going to go to y equals, and in for y1, I'm going to put 4 to the power of 2x plus 6. And in for y2, I'm going to put 3 to the power of x plus 5. And we're going to still get the same answer as we did before. We just have to set a window here. I'm going to make my x values go from -5 to 5, counting by ones, and I'll do the same thing for my y's. I'll go from -5 to 5, counting by ones. I'm going to change my x res to 3 so that it loads a little bit faster, and I'm going to hit graph, and I'm going to end up with 2 curves. Now I don't see the intersection between these, so I'm going to have to create a larger window here, and what I'm going to do is make my y max, let's try 50. Alright, so I do end up with an intersection of both of these. In order to find that intersection, I'm going to press second and then trace, go to intersect. It's going to ask me to select my 2 curves and make a guess of where that intersection is. And there's my answer. For the x value, it is -1.867. Oops, 867. And the y coordinate, oops, I'm sorry, 687, not 867. 687. And the y coordinate really doesn't matter for us then because we're only concerned at what x is. So this is what my x value is. So instead of going through all that work that we did before, we still obtained the same answer in this problem, but this way was solved using a graph. And I'm going to do one more of those. So what I'm going to do is go to y equals again. And instead this time I have 2 different equations. So in for y1, I'm going to put, instead of 1/2, I can use 0.5 to the power of 4x. And then in for y2, I'm going to put 2 to the power of 3x minus 3. So we still could do this algebraically, but we're just going to do this with the graph. I'm going to hit graph and see if my current window is going to work. And let me zoom in actually a little bit more. I'm going to do a standard window here, and we'll see if this shows up. So my one curve is coming down. That's one that had the half as a base number. Then I have another curve going up. So I'm going to have a really small answer somewhere where those 2 curves are going to intersect. So I'm going to press second and trace. Again, go to intersect. And first curve, second curve. My guess is somewhere in that region. And there's my x value. So that is our answer. X is 0.429. And just to show you again, what we really could do if we wanted to check our answer is I could substitute that value in for x. And I'm going to do that just to kind of make sure that this process does work. So I could take 0.5 to the power of 4 times that answer that we got, which was 0.429. And I'm going to get this number. So this represents the left-hand side of my equation. The right-hand side would be 2 to the power of 3 times that number, which our answer was 0.429. And then I would subtract my 3. And I'm going to get something that's pretty darn close. Again, because of rounding, these answers are a little bit off. But both of these answers, both of those values would really be the same since we did solve the equation correctly, and this was our answer. So last problem that we have is kind of the application of using logarithms as inverses of exponential functions. Jess has $2,500 invested in a savings account that earns 4.3 interest compounded quarterly, so that'll be 4 times in the year, and we want to know how long it's going to take for her money to double. So what I'm going to do is write the equation a of t equals, you start off with our initial amount, 2,500. In parentheses, I'll throw 1 plus my interest rate as a decimal, which is 0.043, over the number of times that it's compounded in the year, to the power then of that number of times it's compounded, times t, which is time. So now we have an independent variable that is up in the exponent. And I want to know how long it's going to take for the money to double. So when is it basically going to turn into $5,000? So traditionally what we've done is take this purple equation right here and put this in for y1, put the 5,000 in for y2, and what we'd really do is just look for how long it's going to take for those two values to intersect. So what I'm going to do a little bit differently now is solve this with logs. So I'm going to take the 5,000 and substitute it on the left-hand side of that equation. And that is equal to 2,500 and then 1 plus 0.043 over 4 to the power of 4t. And I'm going to start by doing a little bit of simplifying. I'm going to divide both sides by 2,500 first. And that's going to give me 2 on the left-hand side. And then over here, I'm going to have my parenthesis 1 plus 0.043 over 4 to the power of 4t. And what I'm going to do is clean up the inside of that formula really quick and simplify basically this entire inside. So the left-hand side of the equation is still going to be my 2. My parenthesis value, though, I'm going to take my 0.043 divided by 4 and add 1 to that. So inside the parentheses, I have 1.01075 and raise that to the 4t. So now we can, if I were to really backtrack this and go all the way back to the beginning of this, it's basically what this first example was. We're going to now log both sides of this equation. And if I do that, I can figure out what t is. So I'm going to write log 2 equals log 1.01075 raised to the 4t. And I'm going to bring the 4t down as a coefficient. So I can now have log 2 equals 4t times log 1.01075. Divide both sides by this really ugly log number. And that's where I'm going to go to the calculator. And I'm going to type in log 2 divided by log 1.01075. And I'm going to get another pretty ugly number here. So I'm going to end up with 64.825. And on the right-hand side, I'm really only left with 4t. So all that I have to do then to solve for t is divide both sides by 4. And I get 16.21. So it means that it's going to take 16.21 years for that account to reach $5,000. So again, it's something we had done already, but using the intersection feature, now we can use the algebra and do all this log stuff to basically undo the exponents. So quick recap then, as I go through this, we learned the change of base formula first, and we went through a couple examples of solving exponential equations using logs. And then we solved a couple log equations using exponents, solved some equations by graphing, and then we went through a story problem application.